Welcome back, everyone, to the Algebraic Graph Theory Seminar. This week we have Harmony Zhan talking about the average search probability in a quantum walk with an oracle.
Okay, thanks for the introduction. So the problem I want to talk about today is really motivated by a computer science question. That is, given a database, how can you find a specific point in the database very efficiently? Okay, so in this talk, instead of focusing on the algorithmic side of this problem, I will talk more about the connection between one parameter of this algorithm to the properties of the underlying graph. Okay, so here's the plan for my talk. I will first start with the definition of a quantum walk without and with the oracle. Okay, and the latter case is actually just a search algorithm on a graph. And then the success probability of this algorithm is really just the probability that your quantum walker lands on a particular arc after some measurement. Okay, and then I will define this so-called average success or average search probability and show you that after a series of reduction, this is really just a graph invariant of a subgraph. Okay, and after that, I will apply our knowledge of distance regular graph and to give a lower bound on this average search probability. This lower bound is a function in the intersection array. Okay, and in particular, when d equals 2, we have all the strong irregular graphs. And using that bound, you can show that this probability always converges to a quarter, regardless of the family you lie in. Okay, and finally, I will talk about some open problems. Okay, so let me start with a picture of the graph and a matrix associated with it. Okay, so if you have never seen a discrete time quantum walks before, now you have 10 seconds to spot the connection between these objects. Oh, by the way, these are the indices of the matrix. They are not elements. Okay, so I don't know how you feel about this matrix, but when I first saw it, my first impression was that this is really, really sparse, right? You see many zeros in this matrix and only a few non-zero entries. Okay, and the second thing I noticed is the indices. Okay? They seem to be the edges of the graph, but there are 5 edges in the graph only. And here we have 10 by 10 matrix. So if you take a closer look, you will see that both directions of these edges, they appear in the indices. So in fact, this is a matrix indexed by the arcs of the graph. Okay, so 5 edges gives you 10 arcs. Okay. And the third thing you may notice is that every 2 rows of this matrix are orthogonal to each other. So this is apparent if the rows have different support, right? If the support are destroying for each other. But it's also true for those who do overlap. So for example, if you look at these 2 rows, okay, the inner product is minus 2 over 9, minus 2 over 9, plus 4 over 9. So this sum to 0. Okay, and you can say the same thing for every 2 columns. Next thing, compute the norm of every row, it gives you 1. So this is actually a unitary matrix indexed by the arcs of the graph. Okay, so let's move on. What else can we say about this matrix? Now let's talk about which entry can appear in a particular row or column. So let me pick, let's say this one. Okay, this is a column indexed by an arc 1, 3. It's an outgoing arc of 1. Okay, so what about the rows that actually give you a non-zero entry? We have 0, 1 here. We have 2, 1, and we have 3, 1. So all of these are incoming arcs that enter the tail of the column index. Okay, and the same pattern holds for every other column. If you start with any column, the non-zero entry you will see are only indexed by the incoming arcs of the tail of that column. Okay, and there are many other things you can say about this matrix. For example, you may even find a connection between these denominators and the degrees of the vertices. But I'm going to leave this discussion to the next slide. Okay, so what you see here is called a transition matrix of a discrete time quantum walk on the graph. And in general, if you have a graph, let's call it X, okay? And the state space associated with this graph will be functions that send every arc to a complex number. So in other words, a state is just a vector, and we will always assume it's unit. A unit vector indexed by the arcs. So in this example, you see entry 0, 1, 1, 0, and so on. Okay. And how does this quantum walk evolve? This evolution is determined by a unitary matrix that updates the states. So it sends a unit vector to another unit vector. And as we have seen before, the evolution of this is very easy to describe because this guy is linear. It will be enough for me to just tell you what it does to a standard basis vectors. Okay. So let me pick a basis vector, which is this guy. This means the characteristic vector of a particular arc UV. Okay. So after the action of U, it gets sent to a linear combination of arcs entering U. So let me use different shape. So you see WU, you see the opposite arc, which is EU. Okay, so that's part one of evolution. Part two, what about the coefficients? This is also easy to describe. They are completely determined by the degree of this tail U. Okay, if you know that, you basically know the entire matrix. So the rule is if the arc is not the opposite arc of UV, meaning that W is not equal to V, but is still adjacent to U, then everybody gets the coefficients 2 over the degree. Okay? And for the only arc that's opposite to UV, it gets the coefficients 2 over degree U minus 1. Okay, so now you can use this relation to construct the entire unitary matrix. And this is the matrix we just saw on the previous slides. So let's check, pick the column 1, 0. Okay, so this guy is outgoing arc of 1, which has degree 3. So the denominator should be 3. Okay, and because 0, 1 is the opposite arc, we should have 2 over 3 minus 1, which is exactly negative 1/3. And these two other arcs, they have different tails than 0, so we get just 2 over 3 each. Okay. So I hope that description is clear for now. So we can say many things about this model of quantum walks. For example, you may ask, is there perfect state transfer between two target states? And many questions people ask in continuous time quantum walk can also be asked here. Okay, and the other application of discrete quantum walk is people use it to decide search algorithms. And in these algorithms, the problem is to find a marked vertex in a graph using as few purines as possible. So I need to tell you what a marked vertex means and what oracle means. So a marked vertex is really just a special vertex, and you can put anything on it. Let's say you mark it red, and in reality, you don't know where this vertex is. Okay, but you have an oracle that tells you yes if you have found it, and no otherwise. So the goal is to apply as few oracles as possible to somehow work towards this vertex. Okay. So because our work is described using the arcs of the graph, when we say we land on this marked vertex 0, what we actually mean is we land on these outgoing arcs. So the target here is not a vertex, but the arcs starting from that vertex. Okay, and so in matrix form, the oracle looks something like this. It acts like an identity. Okay, if you have arrived at an arc that's not adjacent to 0, or that's not starting from 0, like even those arcs going into it, they don't count. Okay, so this part, it acts like an identity. And as soon as you land on 0 something, it negates the entry in the corresponding in that vector. So in a search algorithm, we want to apply this oracle O and U alternatively to some initial state. And if the initial state is x0, then the algorithm looks something like O, U, O, U, blah, blah, blah. Okay. So it's helpful to know what this OU looks like. And if you think about it, this is really just the same as U, except for a few rows. So the rows indexed by the outgoing arcs of the marked vertex, because the oracle negates everything in those two rows. So here, I just negate all these numbers. And that is our new transition matrix with the oracle. Okay, so this idea has been applied to many graphs. And here's an incomplete table. The first, maybe most important example is the complete graphs with a loop at every vertex. And in 1996, Grover discovered an algorithm to solve this problem in square root and time. And that algorithm is actually equivalent to a quantum walk on this looped KN. And later, these people, Shelby, Kemp, and Whaley, they generalized Grover's idea to a search algorithm on any graph. And in particular, they analyzed the work on hypercubes and discovered also a speed up. In 2004, Ambanis proposed an algorithm to treat another problem called element distinctness problem. And turns out that algorithm is also equivalent to a quantum search work on the Johnson graph, where K is chosen according to N. Okay, and then there are many variants of these search algorithms. Like people try to modify this algorithm to achieve better results. For example, Tom Wang, who just gave a talk last week, he proposed a so-called lackadaisical quantum walk. So by making the worker lazier, you can arrive at the target with a higher probability. And he looked at the two-dimensional cube, which is just the Cartesian Square of K cycles. And there are also continuous time analogs of these such algorithms. The earliest one, I guess, is in 2004. Trias and Goldstone studied this version on any dimensional lattices. And some strong irregular graphs, including these, and distance regular graph with larger diameters have also been studied in continuous time search algorithms. And finally, there is a more recent paper by Peter Hoyer and Zhan, who studied analytically the lackadaisical quantum walk proposed by Wang on any regular locally arc transitive graphs. Okay, so this list goes on and on. I must admit that this is only what I know about this area. So there are many other papers on this subject, and they use many different models of quantum walks to treat specific graphs. Okay. So what does this search algorithm look like? Well, every algorithm comes with an input, right? And in our case, an input translates into an initial state. So for simplicity, let's suppose the graph is K-regular on n vertices. The initial state should not depend on the marked vertex because we are not supposed to know where it is at the beginning. Therefore, a natural candidate is to start everywhere or start with the all-ones vector indexed by the arcs. And that's just a normalization factor to make it a unit vector. Okay. Now, what happens after t steps is that your new state becomes this guy raised to the t's power applied to the initial state. Okay, so this is again a unit vector. So the squared modulus of every entry gives you a number between 0 and 1, and these numbers sum up to 1. So you actually have a probability distribution. By the way, this is the entry-wise product of the unit vector with its complex conjugate. Okay, so this is a probability distribution. Okay, so in a quantum algorithm, you want to maximize some entries that corresponds to your target. And this is the thing people have looked at in the search algorithms. But we are going to look at something different. So notice that this guy does not converge as t goes to infinity because this is a unitary matrix. So it preserves the distance between two consecutive steps. However, you can look at the average of this probability distribution over the first t time steps. Okay, so this guy does converge to some limit, and more interestingly, you can express this limit using the spectral idempotence of this matrix only. Okay, so that gives you a very convenient way to compute something just based on OU, and then you can feed your computer with this program to ask it to plot the points. Okay, all right. Now, I think every talk on quantum walk will have a slide of spectral decomposition. So here it is. Let the spectral decomposition of OU be this guy. Every eigenvalue of OU lies on the unit circle, so it has to take the form e to the I theta r. Okay, and then let's say Fr is the eigen projection onto the eigenspace of this eigenvalue. Then you can show that average distribution over the period of time that we just defined here, as t goes to infinity, it converges to this very simple formula. Okay, so to compute it, you just do three things. First, compute the product of each eigen projection with the initial state. Okay, and two, you take the squared modulus of every entry. And three, sum this up over all distinct eigenvalues of OU. Okay, so that is a program. Okay, now send this to a computer and ask it to compute the average distribution of K4. Okay, so by the way, this is a marked graph. So 0, 1, 2, 3, and I'm marking vertex 0. Okay, and this guy has 12 arcs, so the distribution will have length 12, and you can see on the outgoing arcs of 0, which is the marked vertex, the probability is slightly larger, and also true for the incoming arcs in this particular example. So 3, 0, and 2, 0, and all the other entries are smaller. Okay. So for our purposes, we won't be interested in the entire distribution. Rather, we will just pick out the entries indexed by the outgoing arcs. So let's sum this up. It's roughly 0.31. Okay, so this is the average probability that my algorithm has find the target 0. So 0.31 for K4, not too bad, not too good. Okay, but in general, you can look at the corresponding entries, take the sum, and compute this probability very easily use a computer. So let's see what this is when n gets larger. Okay, so here is a plot for that probability for K. This corresponds to K2, because if you only have one vertex, there's no meaning to search that vertex, right? And for K2, this is 0.5, which is not very impressive because it's equivalent to flipping a coin. And when n gets larger, it slowly drops. And it looks like it's gonna drop all the way to 0 if you just look at the first few points. But then once you plot more and more points, you realize it's not the case. Actually, as n gets large, these points get large, it gets closer and closer to an asymptote line, which is a quarter. Okay, so that's a very interesting phenomenon. And if you think that's just something special for Kn, I'm going to show you more examples. So here I have the Cartesian Square of Kn. Okay, when n equals 2, you have 4 vertices. And this is just 1/4. Again, not very impressive at the beginning, but then it immediately dropped down to below 0.23. And then it bounces back and gets larger and larger. If you include more points, you will see it still converges to this line. Okay. And here's the plot for the line graph of Kn. It follows the same pattern, starts high, drops below 0.25, and then gets back to this line. And the lattice square graphs, you also see a very similar pattern. Finally, I want to show you the Paley graph. Okay, these graphs are only defined when the number of vertices is a prime power and when it's congruent to 1 mod 4. So you will see these points are more spread out compared to the previous plots, but you can still see the pattern, right? It's getting larger and larger, and then somehow it seems to stabilize at this point. So here's the obvious question. all these graphs are slightly regular, but they have different parameters. Why, regardless of the family, these points always converge to the same number? And to understand that phenomenon, we need to know more about the spectral idempotency of OU. So here comes the technical part of this talk. Okay, so in general, we can't analyze the unitary matrix like an arbitrary unitary matrix, but we can if this matrix lies in some nice group or nice algebra. So you can verify that this OU we defined is actually a product of two reflections. So this means a Hermitian matrix of order 2 or a Hermitian involution. Okay. And the first evolution is very simple. It's just a permutation matrix that maps your arc AB to the opposite arc BA. And this is usually called an arc reversal matrix. So clearly that's an evolution and it's symmetric. What about the second reflection? Well, it's supposed to send an outgoing arc of a vertex to the linear combination of outgoing arcs of the same vertex. Okay, so upon reordering of these rows and columns, you can write R2 as a block diagonal matrix, where every block is indexed by the outgoing arcs of the same vertex. Okay, so let's say the marked vertex is the first one. So, okay, so the top block is gonna be different than the others because of this oracle. Okay, it's exactly the opposite of all the other blocks, but every block is a Hermitian involution. So R2 is actually involution as well. Okay, so that's verified. Now there's a famous result saying if a matrix lies in, if a matrix is product of two reflections, then the state space is just a direct sum of the invariant subspace of these two reflections, which have dimension at most two. Okay, so to find the eigenvectors of this unitary matrix, you just need to do two steps. Step one is to find the invariant subspaces, and step two is to diagonalize OU inside each of these 1 2-dimensional subspace. And at that point, you are just trying to solve a 2x2 linear system. Okay, so those are doable. And I will omit the details and just tell you the result. What are the eigenvalues of OU? The real eigenvalues must be 1 and -1. There are no other choices because they have to lie on the unit circle. The non-real eigenvalues, they come in conjugate pairs because OU has real entries. Actually, the entries are rational. Okay. But more interestingly is the connection between these eigenvalues and a graph obtained from the original graph by adding some vertices, edges, and weights. Okay, so I will show you using an example what this augmented graph is. So take the Peterson graph, mark the first vertex 0. Okay, because the graph is 3 regular, I'm gonna duplicate this vertex 3 minus 2 times. So that's just 1. Okay, so duplicate this vertex 0. So then I have to join it to the same neighborhood. Okay, and that's the augmented graph. What about the weights? Again, 3 regular means I want the weights to be third root of unity. I over 3. Okay, and then I will assign these powers to, so the zeros power of W, W, and then W squared to these 3 arcs. And the opposite arcs will just be their conjugate. So omega squared, and then this will be just omega. Okay. And do the same thing for the other, the original vertex, but in different order. So here I'm gonna put 1, this will be just omega squared, and then this is omega. So the inverse arcs will be 1, conjugate of omega squared is omega, and conjugate of omega is omega squared. Okay, so this is a weighted graph, but it has a Hermitian adjacency matrix. So all its eigenvalues are real. And in general, if you have a K regular graph, then you can construct the Hermitian adjacency matrix in the following way. Take the K by K Fourier matrix, throw away the first column, then the rest of them will contain K's roots of unity. And now in your adjacency matrix, you replace the first row, which should be the row that indicates the neighbors of the red vertex. You replace that by K and K conjugate transpose, and keep all the rest as before. So this A tilde gives you the adjacency matrix of that weighted augmented graph. Okay, so why does this graph help? Well, if you compute the eigenvalues of A tilde, okay, and divide all those numbers by the valency of the original graph, then you will see this. Okay, and they are somehow related to the eigenvalues of the big matrix. So this is a list of eigenvalues of U. We see plus minus 1, which is as expected. And we see some complex eigenvalues in conjugate pairs. But now all the real parts, they are exactly the eigenvalues of that smaller matrix, right? Okay. And once you know the real part, because these eigenvalues lie on the unit circle, you have only two choices for the complex, for the imaginary part, and both of them appear in this list. So what we are saying is here, once you know the eigenvalues of the A tilde, you can recover all the eigenvalues of all U. Okay, so that is a very nice correspondence between the spectrum. And you can also lift an eigenvector of A tilde to an eigenvector of OU. But the lift is a bit complicated through some incidence matrices, so I will omit the details here. But let me summarize what we have done. We have translated the problem on this huge matrix, which is indexed by the arcs. So if you have n vertices and degree k, then this will be the size of the matrix, to a matrix that's roughly the size of your original graph. Okay, and using spectral information about A tilde, you can recover everything about OU. Okay, so the thing we are particularly interested in recovering is this average search probability. So just to remind you, this is the formula. X naught is just a scalar multiple of all one's vector. So we're taking basically a column sum of the matrix. And this FR is the projection onto the R's eigenspace of the transition matrix. So you see that to compute this quantity, everything boils down to the the row sum of FR1. So what is this equal to? And depending on the eigenvalues, you have three cases. So if the eigenvalue is 1, then this eigenprojection does not contribute anything to the search, because all its eigenvectors are solved not 1. And if the eigenvalue is complex, then we have seen that they are determined by the eigenvalues of A tilde. And even better, if the graph is DRG, then this column actually lies in the column space of the lambda. Actually, it lies in the lambda eigenspace of A tilde, and it takes this special form. So you can even express this out using just lambda and thetas, but the formula again is too complicated, so I won't include it here. And finally, what about the eigenprojection onto -1? This eigenvalue does contribute to search, but you can obtain that eigenspace by subtracting all the other eigenspaces from the identity. So this number can be obtained from 1 and 2. Therefore, the key thing we want to work out is bullet point 2. So what is FR1 when the R's eigenvalue is a complex number? In other words, what is this? Okay. Okay, so here's the magic that works for any distance regular graph. And thanks to Ada, now I realize that this works for any graph lying in the both-mass algebra and of a association scheme. Okay. So the first lemma is very simple. What it says is when you take the power of A tilde, you take any integer power and truncate matrix into the weighted part and unweighted part, then that's the same as the vector 0 and the row sum of this the same power of A of extra A. So this is the vertex-deleted graph. You remove A from the original graph and you take the usual 0, 1 symmetric adjacency matrix. Okay, so what that means is for any polynomial in A tilde, after this transformation, it translates into the same polynomial in the recency matrix of the vertex-deleted subgraph. Okay, and then as a special case, the eigenprojection into the lambda eigenspace of A tilde is also a polynomial in A tilde, right? Let's say the polynomial is P tilde something. Then by this lemma, the right-hand side is really just 0 and the same polynomial applied to the recency matrix of X sharp A. Okay, and now it's an exercise to show that this polynomial happens to take A to the corresponding eigenprojection of the smaller matrix as well, if lambda is indeed an eigenvalue of X sharp A. And it sends this matrix to 0 if lambda is not an eigenvalue. Okay, so that is compatible with our expression here, because if lambda is not eigenvalue, this projection is just equal to 0. Okay, so that's an interesting reduction. So as a result, to determine the average search probabilities, the only eigenvalues that contributes to that quantity are -1 of this unitary matrix and the complex eigenvalues, which we now know depends only on the 0, 1, the recency matrix of this vertex-deleted subgraph. Okay, and moreover, you can express that probability as the sum of two terms, where the first term is associated with this -1 eigenspace, and the second term is associated with these complex eigenvalues. And we can even write out S1 and S2 specifically using the eigen information of X sharp A. So lambda lies in the spectrum of a X sharp A. And E lambda is just the corresponding projection. Okay, so let's play with these two formulas a little bit using the spectral decomposition of Km. So for a complete graph, when you drop a vertex, you get another complete graph with a size one smaller than the previous one. So we know the eigenvalues are just the valency and -2, okay, and -1. And this will be the corresponding eigenprojections. So everything in these two formulas are known. Okay, you can plug them in, and it turns out S1 and S2 are just functions in your size of the graph. Okay. Now, if you divide S1 by n, well, this converges to a constant divided by n, so it disappears. It doesn't contribute to search in the limit. And divide S2 by n, this is 1/4 as n goes to infinity. So that explains why for complete graph, the average search probability goes to 1/4 as the size increases. Okay. Now, what about other graphs? Before I proceed, let's just summarize what we have done. We have translated the problem on this arc by arc matrix to a problem on the augmented graph. And if the graph is distance regular, then we can further translate into a problem on the vertex-deleted subgraph, which is much nicer now. And then we have to find a formula in terms of its eigenprojections and eigenvalues. So now you can forget about this unitary matrix, forget about this weighted graph, forget about any ways I put to it. Everything becomes just a graph invariant of this X sharp A. Okay. Now we can say more about these two terms. If you remember the calculation we did for Kn, S1 actually vanishes after you divide it by n, right? And that's not a coincidence because of interlacing. Okay, so when you remove vertex from the graph, and if the graph is regular, then you know the eigenvalues of X sharp A must lie strictly between -k and k. Okay, so what that means is this denominator is between 0 and 2k strictly. Okay, so this guy is at least 1/2. Okay, And now in this second term, the only thing that depends on lambda is E lambda. So I can bring this to the outside, bring this to the outside. And the sum of all the eigenspaces is just equal to the identity. So that tells me that S1 is upper bounded to 1/4, which is a constant. And then by squeeze theorem, you know S1 over N has to go to infinity. So in the limit, S1 does not contribute anything. So we can forget about that thing as well, okay? And now the tricky part is to find the lower bound for S2. By the same argument, well, S2 is slightly more complicated, but I can split this into two terms, so K times K squared, okay? And because the eigenvalue lies between minus K and K, this part, K squared over K plus lambda squared is at least a quarter. So I can bring that out. Now, the 1/4 is the reason why you see those plots approach that line, okay? And what about the rest of them? Let me rewrite this as an entry of some matrix. So well, this is just A transpose is equal to the all ones matrix, and then I'm just rewriting this. So I don't know how you feel about this expression, but when I saw this, I was like, this looks very, very familiar, and definitely have seen something like that before. It turns out I was wrong. What I saw is not this expression, but is E lambda J E lambda. Okay, so if you have worked on continuous time quantum works, you may realize that this is really just the average state of the quantum work on the vertex-deleted subgraph. Okay, so just to provide some background, a continuous quantum walk on the graph is defined using the recency matrix of the graph. So at time t, the transition matrix will be exponential of I times t times a. Okay, and if your initial state is presented in a density matrix, that is a trace one positive semi-definite matrix. For example, if you start with A, E sub A, then this density matrix will be E transpose. Okay, then after t steps, your new state will look something like this. So ut times your density matrix times your minus t. And this is your new state. Okay, as before, I can take the average of this number over a time period. But this time I have to use the integral instead of sum because the time is continuous. However, the result doesn't change. It still converges to a limit, and you can express the limit using the idempotence as well. Okay, so this is called the average state of a continuous time quantum walk. So in our previous example, the D is equal to J. Well, there is a normalization factor, but it doesn't really matter. Okay, and the average states and a related topic called averaging mixing matrix have been studied a lot by Chris and his students and postdocs. And here are these many papers that you can check if you're interested. So at this point, my question becomes, how exactly is the average search probability related to this quantity, right? And here's a summary. I have gone all the way towards this stage, but it's not clear how they are related because the quantity I'm looking at is not exactly the average state, but rather K over K minus lambda, E lambda, J E lambda. So how can I get rid of this? Or can I do some trick to isolate this term? And the answer is yes. Okay. And here the trick is to realize that each E lambda is an idempotent that are orthogonal to each other. So I can actually isolate a copy of this average state in this form, because when you expand these two sums and multiply out, the only term that survives are E lambdas that have the same eigenvalue. Okay, so this is what we are familiar with. What about this? Now that we have written the sum as a sum of a function in the eigenvalues, followed by the eigen projection onto that eigenvalue, then I can view this as the spectral decomposition of the same function applied to the recency matrix of X sub A. Okay, so this is, well, an inverse application of spectral decomposition. And what's more, I can write this a submatrix of the Laplacian matrix. So this is really Ka minus Ax with eighth row and column deleted. Okay, and that term is exactly the Laplacian matrix of X. Okay, so what we are really looking at is the inverse of a submatrix of the Laplacian. Okay. And clearly this guy commutes with its own projections, so I can push it into the second bracket until it hits J. Okay, so now my question is, what are the entries of this matrix, right? If I can find the minimum entry, let's call it alpha, then this guy is at least as large as alpha times J. Like you compare these two matrices entry-wise. And so then I can bring the alpha outside and say that this is at least alpha K times lambda, E lambda, J, E lambda. Okay, so there we will have a lower bound of S2 in terms of really this average state of continuous work. Okay. Now to understand this, we can use many nice properties of the Laplacian matrix. Okay, so the most famous one that probably everybody knows is that the determinant of this matrix counts the number of spanning trees of the original graph, and that's called the matrix tree theorem. But in this talk, we are not going to use that property. It's just something that I feel nice to list it here. And the second property we can use is by the short complement, the inverse of this guy. Okay, you can express it using the original Laplacian matrix in this form. Okay, so this first matrix is n minus 1 by n. This matrix is n by n. This matrix is n by n minus 1. Okay, and the middle block here is usually called the pseudo inverse of Laplacian. Because we know L has a 0 eigenvalue, so it's not invertible, but you can invert all the other eigenvalues and combine that with the corresponding eigenspace. Then these two are equal, and it's called the pseudo inverse. It has some applications in physics. And so using this formula, you can show that the quantity we're interested in, which is L drop A inverse times J, is really just the eighth column of that matrix. Okay, so now everything is in terms of the original Laplacian. Furthermore, if the graph is distance regular, then you can use intersection arrays to easily solve this system of equations. In particular, you will notice that the entries of this vector, it decreases in distance from A. So what I mean by that is if the vertex that indices this column is at distance I from A, and the vertex indexing this column is at distance I plus 1 from A, then this entry, the top entry, is larger than the bottom entry. And you can solve for all these entries explicitly. Okay, so after some calculation, I have found the minimum entry of this vector, which is n minus 1 over nk. And again, this is the size of graph, and k is the degree. Okay, and that implies a lower bound of S2, which is this. Okay, so as n goes to infinity, this goes to 1/4. So that's our target number that we want to show is actually the limit of the average probability. So the question is, does this converge to 1 as n goes to infinity? Okay, I don't know for now, but yeah, this is just a summary saying we have reduced a problem on the discrete time quantum walk to a problem on the continuous time quantum walk on a much smaller matrix. Okay, and I'm very happy at this point. Okay, so for a graph with some nice structures, let's say it has an equitable partition, or even better, it's distance regular, you can find the eigenprojections of the vertex-deleted subgraph using a smaller matrix. So let's say you have a strongly regular graph of parameter nkac. So k is the valency, a is the number of common neighbors of two adjacent vertices, c is number of common neighbors of two non-adjacent vertices. Then the graph x itself has an equitable partition, which is a distance partition relative to a. Okay, and the same partition is also equitable for the vertex-deleted subgraph. So this is the adjacency matrix in terms of this intersection arrays. Okay, now, as for the eigenvectors of X drop A, there are only two types of them. Okay, the eigenvectors, they either sum to 0 in each class of this equitable partition, which means they will be orthogonal to all one's vectors. So these eigenvectors do not matter because they don't contribute to search. Okay, or the eigenvectors will be constant in each cell, and in which case they can be lifted from eigenvectors of this smaller quotient matrix. Okay, so now we have reduced the problem even further to just a 2x2 linear system. Okay, and you can solve this system and realize it has two eigenvalues in terms of these K, A, and C parameters. And these are just the entries of the eigenprojections. So the average state will be the sum of this guy, which will just have two terms, and after some simplification, it boils down to this ratio. Now, what do we know about A and C? A and C counts the number of common neighbors. So they are both less than K, meaning that they will be at most linear in K, right? So the first terms in both denominator and numerators are quadratic in K. And the remaining terms are all linear in K, right? So as K goes to infinity, this guy converges to 1. And that finishes our proof. So for any family of strong irregular graph, regardless of the parameters, the average search probability will approach to at least 1/4. And of course, it cannot go larger. So this is exactly the success probability. I guess I'm almost running out of time, so I'll be quick. Now, the question is, what happens to larger diameters? Well, as before, this graph is DRG, so it quotients down to a path with D+1 vertices. And this is what the path looks like if you know the intersection rate. Okay, so there may be some loops at each vertex, and the weights are the A's. And the directed path will have edges with weights B0. This is the forward edge, and C1, B1, C2, and so on. So X drop A now quotients down to this path with the first vertex deleted. So you can compute the average state of X drop 1 using spectral information of this. But as D gets larger, this can get very tedious to compute. But we have a lower bound in terms of the intersection arrays and the simple polynomial. So here the trick is to consider not this blue path, but an even shorter path, which you obtain by chopping both the first and the last vertex. So this will be a path on D-1 vertices, and its characteristic polynomial is given by a determinant of this. Okay, and let's say, let's call this PV. Then I can show that the VV entry, which is the quantity we are interested in, of the average state of X drop A is at least as large as this number. So the top thing is just you multiply all the intersection numbers except for the first two. Okay, and then denominator is P, the derivative of P evaluated at the valency squared. Okay, so now this is a very simple quantity. If you have a specific family, you can plug this in and see what the number approaches as n gets larger. So I've played with that for many graphs, including Henning graph, Johnson graph. And here's just one example. The Grassmann graph is the Q analog of Johnson graph. And here, the family I pick, it has vertex set, the 4-dimensional subspaces of m-dimensional vector spaces over finite field of order 3. Okay, and as you can see, when n gets larger, when m gets larger, actually, the probability or the VV entry of every state actually gets closer and closer to 1. Okay, and this is also true for many other families, but I don't have a proof in general that the bound actually gives me the limit. Okay, so that is the first open problem that I want to finish this talk with. So number one, can we determine which families of these tensor regular graphs for which the average probability does approach a quarter? Okay, and the bound I provide may not be optimal. There are many other ways to approach this problem. But a relevant question is, some of our techniques also generalize to graphs that are not distance regular, but just have just lie in the Boltzmann algebra of a social scheme. So what can we say if you take, let's say, the second distance graph of a DRG? Okay. And the second problem is more related to the algorithm. So recall that this quantity that we have been computing throughout this talk is actually a limit of the average probability over time period. Okay, so we can talk about the rate of convergence, that is given any small epsilon. What is the minimum integer s, so that for all time step t greater than s, this guy is epsilon close to our limit. Okay, and this is called the mixing time in algorithms, and it's a very important parameter. If the mixing time is small, then that may indicate that the search algorithm is successful. But I don't know how exactly they are related. And finally, I want to talk a little bit about the average state of continuous quantum walks. Although this has been studied a lot, you haven't been really looking at the irregular graphs. So, and here's what I think the connection will be. So a family of graphs is called sedentary if as the family gets larger and larger, the worker tends to be more and more reluctant to leave his initial state in the limit. And Chris has studied this problem in continuous time quantum walks, and I think Tina also has some new result in discrete time quantum walks. But the results are only concerned with regular graphs or even strongly regular graphs. So, I think maybe we can look at irregular graphs obtained by deleting a vertex from some regular graphs and show that while this probability doesn't converge to one, like while this family doesn't behave like a sedentary family, it does converge to some fixed number, and they may be enough to show that average search probability converge to a desired property. Okay, so yeah, that's it. Thank you for your attention.
Thank you very much. Are there any questions for Harmony?
Hi, Harmony. Nice talk. I was wondering if you've looked at the average search probability for the torus.
The torus.
Because I'm guessing it's not going to be 1/4. It should be something smaller. But I was just wondering if you looked to see what it is.
You mean, so do you mean the Cartesian square of Cn, like you join the endpoints of the path and then like the 2D tree?
It's the Cartesian square of the cycle.
That's a very good question. I haven't looked at it, but
Okay.
I would guess it's also not 1/4. I can run a computation later today and tell you the result.
Okay, thanks.
Yeah.
Harmony,
Yeah.
you were relating the sedentary property to your limit.
Yeah.
But I don't think it's so you've got your limit of 1/4 for all strongly irregular graphs, but I don't think all strongly irregular graphs are sedentary. At least I can't prove it.
Yeah. Okay. So yeah. Sorry, I wasn't being very clear. I mean, the graph doesn't have to be. Yeah, it doesn't have to be sedentary. Like you show there are families where this approaches to a number, let's say 2/9, but that may be enough to prove the search probability is good.
Yeah. Okay.
Because you are looking at well, E lambda, J in lambda, which is not just one entry, but it's kind of you're summing over a lot of entries. So maybe eventually it will approach to 1/4 or something that's large enough for search.
And the second thing is the comment about your last question about irregular graphs. Now, in the course of your argument, you run through, and then at a certain point, the Laplacian appears.
Yeah.
Okay. Yeah. Okay. Now, it'd be nice, and it seems likely that if you did the same thing for irregular graphs, at that point, you probably should get the normalized Laplacian.
Sorry, can you explain that again?
What I'm saying is, at a certain point, you suddenly have the Laplacian appearing.
Yes. Yeah.
And my suspicion is, if you look at an irregular graph, what you'll get at that point will be essentially the normalized Laplacian appearing.
But you're just deleting one vertex, right?
Yeah, then you delete one vertex from that matrix. But I mean, so it would seem likely that instead of Laplacian, you would get the normalized Laplacian.
Okay.
Because it's the normalized Laplacian that sort of governs classical continuous walks on the graph.
I see.
Now, that is not necessarily a help, because then you suddenly discover that your film is a bit more complicated, but still it would be nice to relate it.
Okay, yeah, thanks. Yeah, I was wondering like how the Laplacian can actually play a role in relating this work and the classical random walk. So that might be the connection.
If there are no more questions, let's thank Harmony again.
I have another question if Harmony has time. So I guess something that I thought about, which I was wondering if it relates to this work, which is on what graphs does the search algorithm behave similarly to search on the complete graph? So basically, if you look at the complete graph's success probability, not time average, just what the success probability is with each step, then it goes up and down and up and down, and it's like periodic. So if you do search on the hypercube, then that plot looks almost exactly the same as it did on the complete graph, or on strongly regular graphs, it's like the same evolution. And so because that up and down looks the same, if you time average it, you should get the same thing, which you found to be 1/4, which is really interesting. So I was wondering if your question really just comes down to does it come down to on what graphs does search behave like the complete graph?
Yeah, I think that's a very good point. Yeah, so if the instantaneous probability, it behaves like periodically, then when you take the average, it seems like you are just taking the average. I mean, well, I don't know if it's exactly the area or something like that, but yeah, it makes sense that if they behave similarly, then the average will be the same. Yeah. But yeah, I don't know how to compute this. The problem is because well, you see in the average search probability, everything boils down to the eigenprojections only. But if you look at the instantaneous ones, you have to look at the eigenvalues raised to a particular power. And then at that point, I was just lost. Yeah. So yeah, but yeah, I agree. I suspect there's a connection here. Yeah.
And that's why I brought up if you look at search on the grid, because the grid will evolve differently, right? Instead of reaching a success probability of 1/2 before going back down and being periodic, it will reach a smaller probability. So that for sure is going to be a smaller time average. It's just simplest example that came to mind that behaves differently from the complete graph.
Yeah, I've also thought about this question for the average state for irregular graphs. I think maybe I have checked that thing for the grid. I don't remember anymore, but I also checked for the past. Definitely they don't converge to 1. So yeah, so this might be another reason why it fails on the grid.
And for irregular graphs, I guess the complete bipartite graph would be the easiest irregular graph, I'm guessing.
Yes.
So that would be a simple thing to explore.
Sounds good.
Yeah, thank you.
Thanks.